let's study about meter bridge. Meter bridge is a device which is used to find the unknown resistance. It works on the principle of balanced condition of Wheatstone bridge. Let's study what are the components of meter bridge. It consists of a uniform wire of length 1 meter. This wire is stretched on the wooden board. So you can see the wooden board. So this is a wire which is made up of alloy. It is stretched on the wooden board and there is a meter scale over here. The ends of this wire is connected to a thick metallic plates. So it provides a terminal, that is terminals are A and C. Though this is a terminal A and this is a terminal C. So same thing I can represent it over here. This is A and C. Now the unknown resistance is connected in the left gap of the meter bridge. So I can consider a unknown resistor of resistance, some resistance as R is connected in the left gap. Now the resistance box is connected in the right gap of the meter bridge. Resistor of resistance, that is S, is connected in the right gap. Now the strip B is connected to the galvanometer. Then from the galvanometer it is connected to the sliding contact or jockey. The terminals A and C are connected to a cell of EMF E. Now let's see the circuit diagram of meter bridge. So as I explained earlier, this is a meter bridge circuit diagram. So the length of the wire is 1 meter or 100 centimeter. There is a meter scale here. The left side is connected to the unknown resistor and the right side is connected to the resistance box. From B it is connected to the galvanometer and from the galvanometer it is connected to the sliding contact. Now let's consider the sliding contact. As you can see arrow over here, this sliding contact is moved from one end of the wire to the other end of the wire until the galvanometer shows a zero deflection. So let's consider the sliding contact is moved from A. It is moved on the wire. Okay. So at some point the galvanometer is showing zero deflection. Let's consider this galvanometer is showing the zero deflection at point D. So which means the current through the galvanometer is 0. That is also called as the null point. As we have adjusted the position of the sliding contact on the wire, we have found the position D where there is no deflection in the galvanometer. Now there are 4 arms, that is A, B, one more is B, C, C, D and D, A, which forms Wheatstone bridge. Now we can say that the bridge is balanced. Let us consider this distance, that is A to D, as L1 and BC is the total length of the wire is 1 meter or 100 centimeter. So the remaining distance is 100 minus L1. Okay. Now as we know, AD equal to L1 centimeter, DC equal to 100 minus L1 centimeter. Let's consider the resistance per unit length of this wire as RCM. So RCM is the resistance per unit length of the wire. We know the condition for the Wheatstone's bridge, that is R1 by R2 equal to R3 by R4. This is a balanced condition of Wheatstone's bridge. So from this we can write it as, that is AD divided by BC. So this is AB divided by BC. AB divided by BC, that is equal to, the next arm is AD and DC. So we can write it as AD divided by DC. So AB is nothing but R and BC is nothing but S. So we can write it as R by S is equal to AD is L1 and DC is 100 minus L1. So let's substitute for AD and DC. AD is RCM into L1, that is the resistance of the length AD is RCM into L1 and the resistance of the length DC is 100 minus L1 into RCM, 100 minus L1 into RCM. So we can see here RCM is there in the numerator as well as in the denominator. We can cancel it out and we can write it as R by S equal to L1 divided by 100 minus L1, or R equal to S into L1 divided by 100 minus L1. So R is the unknown resistance that we can find out using the formula R equal to SL1 divided by 100 minus L1. Potentiometer. Potentiometer is a device which is used to compare the EMF of the two cells, and it is to find the internal resistance of the cell. Now let's study the principle of potentiometer. Potentiometer consists of a wire which is made up of alloy. This wire can vary from, that is the length of the wire can vary from 4 meter or 8 meter or sometimes 10 meter also. This length or the wire is placed on the wooden board. So these segments are parallel to each other on a horizontal wooden board. So as you can see here, this is a wire of length 4 meter. So each of length 1 meter. So from here to here it is 1 meter. So again here it is 1 meter. So 1 meter. So 1 meter. So total length is 4 meter. So this kind of arrangement we can observe over this wooden board. Now let's see the primary circuit of a potentiometer. So A and C are the two terminals where the wires are connected. From A it is connected to the battery, and the other end of the battery is connected to the variable resistor. Then it is connected to the key. Then from the key to the terminal C. Now here what happens is, in order to understand the concept of principle of potentiometer, let's consider EMF of E and galvanometer is connected. So here you can see from A it is connected to the cell, then from the cell it is connected to the galvanometer, and from the galvanometer it is connected to a sliding contact. So what we have to do is, we have to move the sliding contact from A until the galvanometer shows zero deflection. So let's consider the galvanometer is showing zero deflection at some point D. So the distance between A and D, let's consider it as L. So AD is the balancing length, that is nothing but L. So potential difference across AD is given by the expression IR, where I is the current flowing through the wire and R is the resistance for a length L. This potentiometer basically it works on the principle that the fall in the potential across any portion of the wire is directly proportional to the length of the portion provided the wire is of uniform area of cross section and the constant current flowing through it. So, potential difference across AD is given by I into R. But we know the expression for resistance, that is R equal to rho L divided by A. In this case, we know that rho is the resistivity and A is the area of cross section. Resistivity and A and L is the length, nothing but the balancing length. So let's substitute. So potential difference across AD is equal to I into R, that is rho L divided by A. So this is nothing but V, potential difference across AD is nothing but V. And in the right hand side, you can see here, I is there, I is constant, rho is the resistivity of the material. So this is a wire, so the resistivity remains constant and area of cross section is also remain constant. So the term I rho divided by A is constant. So we can say that this V is proportional to the balancing length. So V is proportional to balancing length, or I can write it as V equal to phi into L, or we can write it as V by L equal to phi. Phi is nothing but potential gradient. So phi equal to I into rho divided by A. So we can understand from here, that is V is proportional to L. V is proportional to L, which means the potential across any portion of the wire, across any portion of the wire is directly proportional to the balancing length. So V is proportional to L. Now let's study the comparison of EMF of two cells using potentiometer. This consists of primary circuit, that is from terminal A, it is connected to the battery. From the other end of the battery, it is connected to the variable resistor, then to the key 1, and from the key 1, it is connected to the terminal C. In order to compare the EMF of the two cells, we should have the two cells of EMF E1 and E2. So let's consider two cells. The EMF of first cell, let's take it as E1, and the second cell is E2. E1 is connected to a key 2, and E2 is connected to key 3, and they are connected to a galvanometer, and from the galvanometer it is connected to the sliding contact. Now we will close key 2 so that cell E1 is connected to the galvanometer, and we'll move the contact from terminal A on the wire until the galvanometer shows zero deflection. That is, we have to move the sliding contact from terminal A. We have to move the sliding contact on the wire until the galvanometer shows zero deflection, which indicates the current through the galvanometer is 0. We'll consider some point over here. That point we'll consider it as N1. N1 is a point where we get the zero deflection. So the distance between A and N1, let's take it as L1. Now we have to apply KVL to the loop, that is A, N1, G, K2 and A. The potential across the points, that is A and N1, is given by phi into L1. Then comes the galvanometer. So the current through the galvanometer is 0. So it is plus 0. And there comes the cell, that is of EMF E1. So it is minus E1 equal to 0. Or phi L1 equal to E1. Let's take it as equation 1. Now we'll consider key 3 is closed and key 2 is open, so that the cell E2 is connected to the galvanometer. In this case, key 3, that is key 3 is connected to the galvanometer. Cell E2 is connected to the galvanometer. E1 is not connected to the galvanometer. Now, we have to move the sliding contact from the terminal A. On the wire, we have to keep the sliding contact at every point until the galvanometer shows 0 deflection. Let's consider N2 as the point where the galvanometer is showing 0 deflection. Let's consider the distance between A and N2 as L2. That is nothing but the balancing length. L2 is the balancing length. Now, we have to apply the KVL to the loop, that is A, N2, G, K3 and A. So, the potential between the points A and N2 is phi into L2. L2 is the balancing length and current through the galvanometer is 0. So, 0 minus EMF of the cell E2 is E2. So, equal to 0, or simply we can write it as phi L2 equal to E2. Take it as equation 2. Now, we'll divide equation 1 by 2. So, we get phi L1 divided by phi L2 equal to E1 by E2, or phi cancels. So, we can write it as E1 by E2 is equal to L1 by L2. Let's study about internal resistance of a cell. It consists of a potentiometer wire, that is AC, connected in series with the battery, variable resistor and a key K1. This forms primary circuit. In order to find the internal resistance of a cell, we have to connect a cell of EMF E. Let's consider a cell of EMF E and internal resistance R is connected to a resistance box, then connected to key 2, and this together it is connected to the galvanometer. From the galvanometer, it is connected to the sliding contact. Let's consider the key K2 is kept open. Let's move the sliding contact from the terminal A on the wire until the galvanometer shows a 0 deflection. Let us consider some point on the wire on which the galvanometer is showing 0 deflection. We'll consider that point as N1 and the balancing length as L1. So the key K2 is open and the sliding contact is moved. We get the balancing length. At one point, that balancing length is L1. Then we can write the expression for the EMF, that is E equal to phi into L1, where L1 is the balancing length. We'll take it as equation 1. Now we'll consider the key K2 is closed, so that the cell sends a current through a resistance box, and we have moved the sliding contact from A until the galvanometer shows 0 deflection. Let's consider that point as N2. So N2 is a point where the galvanometer is showing 0 deflection, and we'll consider the distance between A to N2 as L2. If V is the terminal potential difference of the cell, then we can write it as V equal to phi into L2. L2 is the balancing length of A N2. Let's take it as equation 2. Now we'll divide equation 1 by equation 2. So we get, that is equation 1 left hand side is E and equation 2 left hand side is V. So E by V equal to 5 divided by L1, 5 into L1 divided by 5 into L2. So we can see here 5 cancels out and we can write it as E by V equal to L1 by L2. We'll take it as equation 3. We know the expression, that is current I is given by E divided by R plus R, where small r indicates the internal resistance, or we can write this expression as E equal to I into R plus R. Also, we know that V equal to IR. So let's substitute E and V in equation 3. So let's substitute the expression for E and V in equation 3. So E is nothing but, that is I into R plus R divided by V. V is I into R equal to, you can see here E by V equal to L1 by L2. So in the right hand side we can see L1 by L2. So I and I cancels out. So we get the expression R plus R divided by R equal to L1 by L2. Now we'll cross multiply this. So we get the expression, that is R plus R into L2 equal to L1 into R. So when we multiply, when we will multiply L2, so we get L2 into R plus L2 into small r equal to L1 into R. We will rewrite this expression L2 into R equal to L1 into R. We'll take L2R to the right hand side. So it will become minus L2 into R. So we can see here R is common in both the terms. We'll take it outside and we can write it as L1 minus L2. In the left hand side it is L2 into R. As we have to find the internal resistance of the cell, that is represented by small r. So R equal to R into L1 minus L2 divided by R. So this is the expression to find the internal resistance of a cell. Or we can write this expression in one more form, that is R equal to R into L1 minus L2 divided by L2 as R into L1 by L2 minus L2 by L2. But L2 by L2 is nothing but 1. So R equal to capital letter R L1 by L2 minus 1. So this is the final expression for the internal resistance of the cell.